All right, these are notes for chapter 27. We're looking at diffraction and interference of light. So I'm hoping you guys will try to do this. Light patterns and fingers. So what I want you to do, see if I can describe it. It's kind of hard. But if you take your fingers, your index finger and your middle finger, and you put them on top of each other, and then you open up really wide, so you have like kind of a curve between them, so your tops of your fingers are together, and then bring them really close together, so it's just a tiny slit. Then hold those up to your eyes, and then point at a light, and you're actually going to see an interference pattern. You'll actually see light and dark and light and dark. And you can turn it the other way, and you can see that you can still see that. It's always parallel to your fingers. It's not your eyelashes. But try it just so you can actually see a real interference pattern. And we're going to talk about today how that comes to be. Now, if you remember your wave tank lab, you remember seeing this, right? Where you saw the waves coming through two double slits and you saw this interference pattern. You can also see it with lasers. If I get a chance when I come back to class, I will show you the laser one, but you'll get to see it in the lab too, so I can't do that demo for you live right now. So a couple things we need to remember that we've learned about already is that superposition is the addition of multiple wave amplitudes, right? So when the two waves come together and they add together, it's called superposition, and it makes that pattern. Constructive interference is when two crests or two troughs combine. That gives you a bright color, light, or what we call a maximum. And then destructive interference is when a crest and trough combine, and that gives you what we call a dark fringe or a minimum. So they call it bright fringes or maxes and dark fringes and minimums. So you'll hear that terminology during this chapter and when you're doing your homework problems. So for coherent in-phase light source, now this is important, coherent in phase. The only thing that you know of that's coherent and in phase that's light is a laser. So this only works for lasers, and here's a nice cool pattern that shows with the light. It looks just like the water one, right? This is our max, we're always right in the center. Then we have a first min, and then we have another max, then we have another min. So in order to figure out where the maxes and mins are, we need to do some math. So the maximum is an antinode. Remember, it's maximum light, maximum displacement. And delta L is path length difference. Delta L is path length difference. So some of the light is coming from here and it's going over here, and then some of the light's coming from here and going here. And the distance to that, it's not the same. Remember, we talked a little bit about that with speakers. So it's the same concept. If those are in phase, if they shift by a whole lambda, it gives you a max. So that's the concept. If the path length difference from this source to this one, right? So if we looked from here to there, and we could draw a line to kind of show that. So let's draw a line to kind of show where that is. And I have a line, I make it red, and no arrow. So if I look at the path length, right, so here would be one path length going to that spot, and then from over here, here's another distance, and delta L would be this one minus that one, right? And that's my delta L. So since they were already in phase, if we shift them by a whole wavelength, if that distance is equal to some multiple of lambda, it's going to be a max. If, on the other hand, it's a minimum, then they end up in one of these dark spots, same concept, right? So if I look at that and I want to make a minimum, right? So I go here to this dark spot, and from here, this dark spot. And I look at the difference in path length, and that's equal to a half a wavelength, right? M plus half, because I can't do 1, so it would be like half if M is 0, and then it would be 1.5 and 3.5 and et cetera, et cetera. Then that may be a minimum, and it would be a half a wavelength out of phase. So there was this guy by the name of Young who did an experiment, so they called it Young's experiment, and he said if you take coherent in-phase light, or he took coherent in-phase light and passed it through two slits, and that's when he got to see that interference pattern, the same interference pattern we saw on the first screen. Again, since they do demo with hair and laser, I can't do that. You guys are going to actually do it in the lab. But it gives you this light and dark pattern. To me, it kind of looks like an airplane. You have this big spot in the middle, and then you see these dashed lines coming out from over it. And so this is a picture showing that path length difference I was trying to show you in the other one, right? So here's slit 1, and here's slit 2. This is the distance between the slits and the screen, so my interference pattern is going to show up on this screen, and you guys will have a card for your screen. And then here's the distance L that we're going from slit 1. Here's the distance going from L2. And then this little blue part right here, that represents delta L, right? That's the path length difference. And that's equal to D, because this is D, and this angle's theta. So you can see that's D sine theta, because that's the opposite side. That's the hypotenuse. So delta L is equal to D sine theta. So over here, the hardest thing for these is keeping track of all the different distances, just the terminology, and people get these confused. So make sure to pay attention. D is the distance between the slits, right here, distance between the slits. L is the distance to the screen, and Y is the distance from the center to the bright, or the min, or the dark, or whatever, but Y is the distance along the screen, right? So we've got 3 distances. We've got the distance between the slits, we have the distance from the screen, right? Because if I move this, right, we know geometry, it's going to change the distances. And then this is the distance over here. And the little m just means 1, 2, 3. Which one are we looking at? And the difference in path length is just this little tiny distance that's right there. So here's some other equations that go along with this, right? We know this path length difference is d sine theta, so it's showing you that right here. So we know if d sine theta equals m lambda, that's going to be a bright. That's going to be a max. We know that if they went straight to the middle, they'd be the same distance, and so that just means m is equal to 0, and that's always a bright. So we usually start with 1. We don't care about the middle one. And then if it's m plus 1/2 lambda, that's a minimum. Now, the one thing you're just going to have to trust me with is that the tangent of theta is also equal to y over L. So if you look at this picture, I found this one, and it's probably the best way to look at it. But see this angle here, there's my one triangle here. Maybe if I can draw on the triangle, you can see it a little better. So here's my triangle here, right? Here's my one triangle. And then my other triangle is here, which is y and L, and then this is going from the center, oops, up there. It's not a very good triangle. But these two thetas, right, are the same. Those two thetas, this theta here and this theta here, are the exact same angle. And so you can see that y over L, right, because this is y, this is L. They call it D here, but that's our L from the other one. Y over L is equal to tangent theta. Now, so this is sine theta, and this is tan theta. But, and if you don't believe me, plug in your calculator. Sine theta and tangent theta are exactly the same value when you get really small, right? Because sine theta is sine theta over, tangent theta is sine over cosine. And so when you get really, really small, they actually end up being almost the exact same thing. It just, trust me. I mean, we're talking small. We're talking like 0.01 degrees or radians. I mean, it's a really tiny number. So I can set this, right, sine theta is equal to m lambda over d. See that? Sine theta is equal to m lambda over d. Do you see that? Yeah? So m lambda over d is equal to y over L. So the equation you end up with is y over L equals m lambda over d for a maximum. If I wanted to be for a minimum, all I would do is change this m to an m plus 1/2. The equation sheet uses x for y. Your book uses y, so we're going to stay with the y, but it's this distance over here. So if you look at the equation, they have this equation on your equation sheet, but that's an x, but it's the same thing. So those are for for double slits. Multiple slits. Again, I want to show you this demo, and when I get back, I will try to show you some of these that we're missing. But with a diffraction grating, you actually end up with many slits. And so instead of just having 1 or 2 or 3, you have many. So what happens is that you have this path length difference happen again and again and again, and so you just get a brighter pattern, but it's the same equations. The equations are exactly the same. It's still d sine theta equals m lambda, and d sine theta, y over L equals tangent theta. Single slit is where it gets kind of weird. The max and the min are reversed. The best way I can explain this is basically the wave comes through and it splits itself in half. Well, since it splits itself in half to interfere with itself, I can't explain it any better than that. Waves are just weird. But it splits itself in half. That means its wavelength basically becomes half of its wavelength. So you end up with the m plus 1/2 being the maximum and the m being the minimum. So all we did is we reversed which one those are. And then instead of a d, it becomes a w because this is the width of of the slit. But otherwise, it's the same thing, right? That's what you do with your fingers, is you actually cause the waves to split and interfere with themselves. So that's multiple slits and single slits. Some uses of this interference that we're seeing is something called an interferometer. So the device uses light interference to measure very small distances. So what you do is you send in a source light, and it bounces off one mirror, and this mirror is like semi-reflective, so it reflects some, but some goes through, and so then it bounces it here. So what happens is you have light that goes from here and light that comes from here, and then they combine together to make an interference pattern. And what they do is you can move this distance, right? So it's showing you that this translates, and this distance can move, and so as this distance moves, you can actually figure out what that tiny little distance is. So it's a way to measure really tiny distances, and they do that a lot in computers and things like that. When I was at IBM, we used interferometers. You put it in the device, and you can move things just a tiny bit or figure out what the separation is simply by this tiny amount, looking at d sine theta equals m lambda, y over L. I mean, everything's the same thing, right? And you're looking at the path length difference now. It's just the distance from this mirror compared to the distance from this mirror. But otherwise, everything's pretty much the same. Resolving power is the idea that you can't tell that two objects are the same until they're a certain distance apart, right? It's kind of like looking up in the sky and you see stars, and some stars are actually binary stars. They're two stars, but they look like one star because it's not resolved, because your eye has a certain opening and it just can't resolve it. So you could use a better microscope that's more powerful, and then you can start resolving it into two. But it's kind of like, or think of it like a car is coming towards you, and you've got the headlights, and if it's really far away, it looks like one headlight. But then as it gets closer and closer, you can see the two headlights. So it's the ability to see two objects as two objects. The smaller the theta, the better the resolving power, right? So this theta is how well you can see it, right? So the smaller this is, the better you can resolve it as something different. So these are the two objects coming in. This is the opening, like it could be the opening of your pupil, it could be the opening of the camera aperture, right? And then these two objects are far away, and they're a theta angular distance apart. So the smaller I can make theta, the better my resolving power. Usually we use the equation without the sign, but you have to do that in radians. If it's a really small angle, right? If it gets to be a big angle, then you really have to go back to sine theta. Gets you more exact answers, but usually we're talking about small angles. The 1.22 comes from the fact that the opening is usually circular. Lambda, right? So the bigger the lambda, the harder it is to resolve, right? Because we want this to be small, and the bigger the diameter, the better it is for resolving, right? So we want the theta to be as small as possible, and we want the d to be as big as possible to give us the best resolving power that we could get.